Hello, Mr. Sorrentino here, doing another video for Math 31, and this one deals with the last section of 3.5, solving equations and inequalities with absolute values. Um, now, well, basically the equation solving strategy, it's not much different than working with basic equations that we learned about and worked with before. Basically using the order of operations in reverse. It's just, we have to do something special to handle the absolute value part of the equation. So these are pretty basic equations. Just have to do something different with the absolute value symbol. And what we do with the absolute value symbol to get rid of it is based off of what you see in this tan box here. If I have some algebraic expression surrounded by absolute value marks, and that's what this big X is standing for, it's some large expression. It's not just a single variable necessarily, but it could be like, a number of terms added and subtracted together and raised to powers and what have you. If it's set equal to a number that's positive, it's the same thing as me saying that that expression equals the opposite of that number as well as x equals that actual number. And that's in absolute value equations will often have more than one answer. So when we look at example 1, scroll this down a little bit, part A, basically for me to solve that equation, I had to get rid of the absolute value mark first. Because the 3 is multiplied to the x, the 5 is multiplied to the x. I can't move them away from the x until the grouping symbol can go away. The grouping symbol is not just a parenthesis here, it's an absolute value, and I have to do something special according to what was in that tan box to get rid of it. And so the only way to get rid of that absolute value mark is to say, okay, well, that means that 3x plus 5 has to equal a positive 11, or 3x plus 5 has to equal a negative 11. And so that's how I get rid of the absolute value mark. I had to split it into two equations. Very most common incorrect answer that students give for absolute value equations is that they'll often forget this one right here. They'll just get rid of the absolute value mark like it was any other parenthesis, and then proceed on just to solve one half of the overall equation. You should expect two answers with absolute value equations, and if you're not getting two answers, there better be a good reason why. And there are some instances where you can only get one solution for an absolute value equation, but it is rather rare. So at this point, all I'm going to do is just solve the two equations. So I'm going to subtract 5 from both sides on both equations. So subtract 5 on the left-hand equation on both sides, I get a 6. I subtract 5 from both sides on the right equation, I get a negative 16. I then divide both sides by 3 on both equations. Doing that on the left equation gives me a 2. Doing it on the right is a negative 16 thirds, which is pretty much the same as 5 or negative 5.3 repeating. This would be a negative. So, I could say that x equals 2 or x equals, I'll just leave it at the negative 16 thirds. And that would be my solution set. So that's something that you have to keep in mind. You should always have two, to get rid of the absolute value marks, you have to split it into two separate equations. And don't forget about doing that, because that is one of the most common errors with these type of equations. Now, absolute value equations, since absolute values do something special, you can have circumstances where you may not have solutions for a given equation. Now, how you recognize that might be in different places. So let's look at B, because B doesn't have a solution. And there's two different places you could possibly notice that. I want to get x alone on one side of the equation. It's always ultimately my goal when I solve any equation. I want to get, for that to happen, I had to get rid of the subtraction of 4 that's attached to the x, but that's attached to the x inside of the grouping symbol, which is the absolute value mark. So I'd have to get rid of the absolute value mark before I get rid of that minus 4. But also, Attached to that absolute value mark is an addition of 7. So I had to make sure that, as we do absolute value equations, that you shouldn't always think that the absolute value mark and getting rid of it is always the first step. Here, it's not the first step. The first step is I had to get rid of that plus 7 in order to get to the point where I just have the absolute value of an expression equaling a number. In this case, it's -1. Now, here is the first instance where if you're paying attention, you could say here, hey, there's no real solution. There's really no imaginary solution either. I could just say probably no solution. But it's safe to say no real solution. And the reason being is, remember, an absolute value mark will always produce a positive result. There is no such number, there's no such numbering system where if I take the absolute value of something, I end up with something that's negative. So right there I can notice that there's no real solution. But say, for instance, you didn't notice it there. Well, you would carry on to work the rest of it how we did it. You would say, okay, well, to get rid of the absolute value mark, I would split it into two equations. X minus 4 would equal that -1, or x minus 4 would equal a -1, which of course is a positive 1. As you solve these equations, I add 4 to both sides. On the left-hand side, I get x equals 3. I add 4 to both sides of the right equation, I get x equals 5. So you're saying, well, I got solutions here. How do I know there's no real solution? Well, this goes back to something you should always be doing irregardless of whether I show it in examples or not, and that's take your solutions and go back to the original equation, make sure it works. So if I go to the original equation using this solution, I would have the absolute value of 3 minus 4 plus 7. Does that equal 6? Well, 3 minus 4 is -1. The absolute value of that is 1. Does 1 plus 7 equal 6? Well, no. 1 plus 7 equals 8. So this is not a solution. If I do it for this one, x equals 5. Well, 5 minus 4, absolute value, plus 7 equals 6. 5 minus 4 is 1. The absolute value of that is 1. And I get to the same point. 1 plus 7 doesn't equal 6. No, 1 plus 7 is still 8. So this doesn't work either. So this solution doesn't produce an answer. The two solutions that I algebraically came up with simply don't work. Now I should make sure to always go back and make sure I didn't make any computational errors or anything like that. But also based on what we said before, the two solutions that came up don't work. So we're back to the same conclusion. There's no real solution for this. And we have to pay attention to that because absolute value equations could, in fact, have no solution. Now, when I get to inequalities and I get to a similar circumstance, no solution is only one possibility. I could possibly have, infinite solutions too. So let's have a look at inequalities. So as I start with absolute value inequalities, you're going to see that this is another instance where I'm going to kind of show something a little different than what the book shows. I'm using a method that the book will eventually kind of resort to when I start getting into polynomial inequalities and other types of inequalities later on in the course. I choose to go to it now because there are some rules that says, okay, like, well, if I have an inequality with an absolute value, then some instances it's going to be an or statement, other instances it's going to be an and statement. And then I have to worry about, having the two separate inequalities, making sure that I'm dividing both sides by a negative. I have to make sure to change the inequality around. Those things can all pop up at various times in these types of inequalities. And that creates a lot of confusion and ends up making a lot of unnecessary mistakes. And sometimes that also causes there to be a great deal more work needed than necessary. So here, I start using a method that the textbook actually starts using a little bit later. And what I'm going to do is, and from any inequalities from here on out, we're going to first solve a similar equation and the similar equation is just simply me taking the inequality out, replacing it with an equal sign. And then craft the solution from the number line. So we're not going to be using we're not going to graph something on the number line as an afterthought like we did in the previous lessons. We're actually going to use the number line to come up with what the actual solution should be. So let's see how we would go about doing this. So example 2a, I'm going to turn this into a similar absolute value equation. So I'm just going to get rid of the greater than and replace it with an equal to. And I just do what I did above. I'm going to solve this equation. So I have 2x plus 5 equaling 7. The first thing I need to do in this equation is get rid of the absolute values because everything is attached to the x is on the inside of that. I can't move them until they go away. So I need to split this up into two separate equations to get rid of that absolute value mark. 2x plus 5 is going to equal negative 7, or 2x plus 5 is going to equal a positive 7. And I'm going to solve each one of these equations. So on both equations, I'm going to subtract both sides by 5. Doing that on the left equation, I get a negative 12. Doing that on the right equation, I get 2x equaling 2. And then for both equations, I'm going to divide both sides by 2. On the left equation, that's going to make x equals negative 6. And doing on the second equation is going to give me x equals 1. So that gets me the two solutions for the equation. I have to keep in mind at this point, this solves the equation, but my original problem is an inequality. I can't just leave it here. And that's a mistake that students will make using this methodology. They'll just solve the equation, call it quits, and say they're done. You're not done yet. Now here's where I use the number line to come up with my answer. Now, I don't draw like a very over-sophisticated number line. I'm going to put two slashes on here, one at negative 6 and one for 1. Because those are where the two solutions to the equation are. And here's what I do. I'm going to pick a number. Well, having these splits this number line into three different segments. I have the segment before negative 6, I have the segment between negative 6 and 1, and I have the one that follows 1. So what I do is I'm going to pick numbers that are each one of these three segments. So a number before negative 6, negative 7 would be a good one. A number between negative 6 and 1, well, 0 would be a good instance. And a number that's more than 1, we'll just say 2. Now I could pick any number that falls in these regions. I'm just using these as representatives. Now, these two solutions, the inequality does not have an equal to sign in it, which means negative 6 and 1 are instances where the left-hand side of this will equal 7. I don't want it to equal 7, I want it to be greater than 7. So these are going to be open circles because equaling 7 is not going to be more than 7. So now I'm going to try some of these representatives. If I use the negative 7 and go back to the original inequality, 2 times negative 7 plus 5, absolute valued, is that greater than 7? Well, 2 times negative 7 is negative 14. Negative 14 plus 5 is a negative 9 absolute valued, which equals 9. Is that greater than 7? And yes it is. So that means that -7 makes the original inequality true, which means anything in this first region should also do the same thing. So I'm going to shade in the number line. 0. If I do the absolute value of 2 times 0 plus 5, is that greater than 7? Well, 2 times 0 is 0, plus 5 is 5. The absolute value of 5 is 5. Is 5 greater than 7? Well, no, it's not. That means 0 does not work in the original inequality, nor would I expect anything in the region where 0 lies. So I do not shade this middle region. Lastly, I'm going to go to use the 1. So 2 times 1 plus 5, or the 2, I should say 2. The 1 was what you took care of. Is that greater than 7? Well, 2 times 2 is 4, plus 5 is 9. The absolute value of that is 9. Is that greater than 7? Yeah, it is. So 2 makes the original inequality work, and therefore anything in the same region as 2 should also do the same. So there is the answer to my inequality for this on the number line. So I use the number line to then state what the answer is. And if I state it in interval notation, my solution in interval notation, I could say that it's all x's with negative infinity up to -7 without touching -7, or to infinity. I could also state it in more of an inequality notation and say that it's x is less than -7 or x is greater than 2. Oftentimes we do ask for interval notation with this just to get you in the habit of doing it for calculus purposes. And also because it's a direct translation of what you see in the number line. So that's the procedure we use for all inequalities after this point. We solve a similar equation, we get our solutions, we put those on the number line to split it into how many ever regions it might split it into, and then I simply test out representatives from each one of those regions and see if it makes the inequality true or not. If it does, I shade it. If it doesn't, I don't. And as a result of that, when I'm done with it, I'll have a graph of my answer, and then I can then interpret it as an answer. So let's look at B. For B, the first thing I have to do, first thing I'm going to do is rewrite it as an equation. See, I don't have to worry about the ands and the ors, and remembering which one's which, and, doing any kind of reversals of, inequalities and when that has to happen and when to make the decision and all that stuff. It's a lot of things to decide upon. It makes the work oftentimes a lot more daunting and certainly a lot of writing. This method reduces the amount of writing you do considerably, even when these get very, very complicated. So for this, I'm going to solve this equation first. Now, I do have a 2 attached to the x through multiplication, but that's inside of a grouping symbol, whereas the +5 is outside of the grouping symbol. I know I need to get rid of the absolute value mark at some point, but if there's stuff on the outside of it on the same side of the equation, that has to go first. So the very first thing I have to do here is subtract 5 from both sides. I will have a lot of students try to get rid of the absolute value first, and then from there, try to solve the equation beyond that. So now I'm ready to separate this into 2 separate equations. That means that 2x would have to equal a -2, or 2x would have to equal a positive 2. And solving this equation by dividing both sides of both equations by 2, I would get that x equals negative 1 or x equals 1. So I got my solutions to the equation. Again, I have an inequality. I have to account for that. So I'm going to set up a number line. I have negative 1 and 1 are the two solutions I got to the equation. I know negative 1 and 1 are going to produce an instance where the left-hand side becomes 7. I don't want it to equal 7. I want it to be less than 7. So again, that's going to generate open circles here. If I had an equal to in that inequality, I would fill them in. Again, I'm going to choose some representatives from the three regions that are now created on this number line. I have those before negative 1, so negative 2 would be a good representative. Between negative 1 and 1, I'm going to choose 0, which is really the only integer in there, but I could choose fractions if I want. I could choose like a half if I wanted to. And one that's more than 1, 2. And so if I go back to the original inequality, and I use the negative 2, I'm going to have 2 times negative 2 plus 5. Is that less than 7? Well, 2 times negative 2 is negative 4. Negative 4 absolute value is 4. 4 plus 5 is 9. Is 9 less than 7? No. So I'm not going to shade that region in. If I use the 0, I'm going to have absolute value of 2 times 0 plus 5. Is that less than 7? Well, 2 times 0 is 0. The absolute value of 0 is 0. 0 plus 5 is 5. Is that less than 7? Sure is. So this middle region is going to get filled in. And for 2, I get pretty much a very similar instance like I had for negative 2. 2 times 2 is 4. Absolute value of that is 4. 4 plus 5 is 9, which is not less than 7. So the right-hand region doesn't work. There is my solution. Therefore, the solution in interval notation, I could say x is between negative 2 or negative 1 and 1. In standard notation, I could say x is less than 1 and greater than negative 1. Either one of those would be sufficient depending on what you're asked to do. A lot of times you will be asked to do it in interval notation just for practice purposes. So that's how we do it with these inequalities. The other inequalities that you're given to have a look at in this example are just to kind of consider some special circumstances. So let's have a look at this. So some special cases for absolute value inequalities, for example 3. So, again, I'm going to rewrite this as an equation. Absolute value of x plus 5 plus 9 equals 2. And I go through the solution process. I get rid of that plus 9 first, and that equals a negative 2. There is no way for the x plus 5 absolute value to equal a negative 2. The equation has no solution. And that's going to be the same for b too. I mean, I'm going to have the same thing. The equation that I create has no solution. So what that means is, for a, if I draw a number line here, I'm not able to put anything on there. I'm not able to say, hey, this is an answer, that's an answer. So basically, if I want to come up with a representative of that region. I can just pick any number I want. I'm going to choose 0. Now, just because the equation has no solution doesn't mean that the inequality is going to agree with that. I chose the number 0 as a representative of something on the number line because the number line is all I have. I don't really have any markings on here to say, hey, this splits it up into so many regions. If I do the absolute value of 0 plus 5 plus 9, is that greater than 2? Well, this is going to be equal to 5 plus 9, which is 14. Is 14 greater than 2? It sure is. And since 0 makes a solution, therefore anything on the number line is going to make a solution. And so the correct solution to this inequality is, in interval notation, I could say x goes from negative infinity to infinity. I could say x is any real number. Or I could say that x is any number. It has infinite solutions. Now, on the other hand, if I have the same instance occurring for this one, and I draw my number line, it's going to be the same result for the equation. I'm still going to get the absolute value of x plus 5 equaling, and that should be a negative 7, not a negative 2. In any case, I'm still not going to have a solution. I'm still going to get the equation to have no solution, but as far as the inequality goes, well, again, I have nothing to split this number line into any regions. And therefore, I'm just going to pick a number that's on the number line. I put 0 in. Now, if I put 0 in, it's the same left-hand side I had before, except now I have essentially 14. Is that less than 2? Well, that's not at all. So I wouldn't be able to shade in any part of the number line. So here's where I would say the inequality has no solution. So just because the equation you solve, that you create, that's similar to the inequality has no solution, doesn't mean that the inequality is going to have no solution. That's one of two options that you could have for that. So for instance, just from more simplistic ones, the absolute value of x is greater than 0. If I solve that, again, I could say, well, the absolute value of x equals 0, which means that when I solve that equation, x equals 0, or x equals negative 0, which negative 0 is the same thing, so I really don't have to consider that one, which means x equals 0. I do have a solution that comes, I can put on the number line. 0. Should it equal 0? No, I don't have an equal to sign on that. So I would say, okay, well, here I have this. I do split this number line into two regions. So I can say, okay, well, I'm going to pick negative 1 for this region, 1 for this region. Again, I can pick any number I want from any two of those regions. This one here, the absolute value of negative 1, is that greater than 0? Well, the absolute value of negative 1 is 1. Is 1 greater than 0? Sure is. I would shade this. For 1, is the absolute value of 1 greater than 0? Well, the absolute value of 1 is 1, so yeah, that works too. So for this inequality, without the equal to sign, any number but 0 works. So I would say this one has a solution. I could say in interval notation is negative infinity to 0 or 0 to infinity, open bracket, open parentheses all the way, or I could just say that the solution is x is any real number and x can't equal 0. For D, it'd be the same equation I'm solving. I would still have a number line, I'd still have 0 on it. The only difference is I'd be allowed to fill in the 0 because the absolute value of 0 equals 0 and equal to is an option. The greater than will work for any of these numbers. Those that are smaller would work as well because they're going to produce numbers that are more than 0 in absolute value. So this one would be negative infinity to infinity, or I could say, x is any real number as a solution. When I get to less than or equal to go, still the same equation is being solved. I still have this equation, absolute value of x equals 0 being solved, so x is going to be 0 is going to be the solution to that. So for this one here, I have x being 0. I don't want x to actually equal 0, so this would be an open dot. And if I pick representatives from here, here's -1, here's 1. Again, the absolute value of -1 is going to equal 1, which is that less than 0? Well, no, it isn't. So I don't shade that part. Same thing with 1. So I don't shade the right, I don't shade the left, and I have an open dot at 0. So this would be an instance where I have no solution. Makes sense too if you think about it. Well, it's basically saying that the absolute value of x is negative. Well, the absolute value of any number is never negative. Just like if I go back to saying what these mean, this is the absolute value of x is positive. Well, that's true for any number except 0. 0 is not a positive number, but the absolute value of 0 is 0. This is saying, well, the absolute value of x is 0 or more. Well, yeah, that's what the absolute value does. Whereas for this last one, same thing as this previous one for E, I'm going to have a number line. I'm going to have my 0 on there, but the difference is this time, x can equal 0. But but if I have 1 and -1 here, it's not going to make this true. I'm going to have values that are more than 0, not less. So this is the only number that'll work for this instance. So this is one of the rare instances where I have an inequality and the solution is x equals 0. It's actually an equation answer. So, if you get an equation answer, it's a very rare occasion if you start off with an inequality and end up with an equation answer. This is one of the few instances that happens. You're not going to see this happen a whole lot, but if it comes down to something that kind of goes in this path, it could. And that's the end of the examples for this and how to deal with absolute value inequalities. And this is a procedure, as I said, we're going to start using for any inequality from here on out. So that's all I have for now. If you have any further questions, please make sure to bring them up in class or come to my office hours. Until I see you in one of those instances or until the next video, I will see you around and have a good day.